What? LOR? LOR? The letter of recommendation.
Let me read.
Let's take 5 seconds. Settle down. 5, 4, 3, 2, 1. That was not quite 5 seconds, but good enough. All right. So as you see, we started. We finished thermodynamics, right? A week and a half ago or so. We did our test, and now we started chapter 22 last week, and also 23 back on Thursday. And so chapter 22 was about charges and forces, and then he touched a little bit on the concept of the electric field. Chapter 23 is devoted to calculating the electric field for various charge distributions. During discussion and lab, we used some integration to find the electric field for a few distributions, which I will list on here. And so we will continue to do that today. We'll discuss the basically parallel plate capacitor and then the dipole moment and how it rotates on an electric field and most of the charge particles in an electric field. Gauss's law is some more on the electric field. It discusses how to calculate the electric field taking advantage of symmetry. Meaning you don't have to do, if you take advantage of symmetry, you don't have to do very tough integrals or lots of integrals. You will do very little work, but you will get a lot of reward. So that's what we're going to do. If we finish 23 today, we're going to start 24. So you see, we're covering quite a lot of material. So basically my advice is don't fall behind. Okay? Don't fall behind. All right, so for the discussion this afternoon, for the one you meet with me, we'll be finishing worksheet number 5. So, and then for other class, tomorrow we will do worksheet number 5. So, during discussion, we derived quite a few formulas. And so for the class that met me yesterday was yesterday, for the other section was last week actually. So I'm going to write down a summary of what we did. We found the electric field due to suppose you have a rod that is of length L, and you want to find, and it's charged, it has a charge Q on it. So everywhere on the rod there are charges, so either maybe plus, 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 or maybe minus, 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 minus. It doesn't matter. If it's plus, the electric field would be away from them, and if they are minuses, the electric field would be towards them. So at a point, somewhere where at the center line of the rod here, halfway, what is the electric field? We found it through some integration, and we argued that the net electric field will be in this direction. The electric field would be in that direction, because you have charge. If you have a charge here and it produces an electric field away from itself, and you have another one here just by symmetry that will produce an electric field also away from itself. So this one is going like northeast, and this one is going southeast. The north part and the south part, or up and down, they cancel, and the only one that survives is the one to the right. Okay? And actually, we did that problem again in worksheet number 5. If you meet with me tomorrow, we will do that. We will redo this problem in the worksheet. Okay, so what was the result? Well, I will write it down. It's not something I memorize. So for this part here, the electric field is equal to 1 over 4 pi epsilon naught. Again, 1 over 4 pi epsilon naught is also known as K, right? And it's basically 9 times 10 to the 9. I prefer to write it as 1 over 4 pi epsilon naught for the most part. Okay. All right, so here, this is Q divided by R, and then the square root of R squared plus L over 2 squared. That's 4A rod. How long is this rod again? L. Good. Then we also did an infinite rod, or an infinite line of charge. If the line is infinite and it has a charge density lambda, remember what lambda was. So let's write down that result. Infinite line of charge. So if it has charge density lambda, lambda is the charge per unit of length. If you like, it's dq dx. How much charge q is within a length dx. And so it looks like this. So if you have a line of charge, you can draw it as a line this way or a line this way, it doesn't matter. To save space, I'll draw it this way. And so let's say we got pluses. So what is the electric field? And by the way, we will derive this, if we get to Gauss's law today, or Thursday, we will derive this result using Gauss's law also. So as long as you're a distance r away from it, you don't have to be at the center, because if it's an infinite line, anywhere is basically the center, right? Anywhere you stand, it's still infinity this way and infinity that way, right? Does that make sense? It's infinitely long. Yeah. So anywhere you stand, whether you're here or here or here, as long as you're a distance r away, what is the electric field? Well, it turns out to be E. Does anybody have it memorized from memory?
No.
Okay. It's 1 over 2 epsilon, 2 pi epsilon naught lambda over r. That's the result. So the point for a point charge, the electric field falls as 1 over r squared. As you go away from a point charge, the electric field drops as 1 over r squared. Falls quite fast. But if it's a line of charge, it drops as 1 over r. It falls slightly slower. Okay? Then we did a ring of charge. So ring. So a ring of radius r and charge q. We found the electric field due to that. So here is a ring, and it has a radius r, and I was thinking I had a ruler or a meter stick. I don't, but if I have an axis here, what is the electric field for an axis perpendicular to the center of the ring? So what is the electric field there? We derived the following formula. So this is the z-axis, and that formula was, again I will write it down. So it was E equals 1 over 4 pi epsilon naught, and then z, and then q over z squared plus q squared to the power 3 times. Hopefully I have it right. Yes, I did. Okay, this is for a ring of charge, right? So imagine you have a ring on the board here, and you're this far away. The question is, what's the electric field at this moment? As long as you're on the axis, well, if you're a distance z away from here, this would be your electric field at that point. Okay? In what direction is the electric field? Well, it's along the z-axis, away from the ring. If the ring is positively charged, if the ring is negatively charged, it would be toward the ring. Okay. Then, yeah.
I thought it was z squared plus r squared.
Oh, yeah, it's not q, it's r. Yeah, thank you. Thank you. Is this good? It has to be, because this one is dimensions of length. I can't have q. Q plus a charge plus a meter doesn't add up. So thank you. Yeah, that's good. By the way, again, don't hesitate. If you see something wrong, or even if you suspect something is wrong, say something. So then we took advantage from last week. You might remember from yesterday, it should be fresh maybe. We took advantage, we said for a disk of charge, a disk we said is many rings, many concentric rings. You start from a tiny ring, and then a ring on top of it, and a ring outside of it, and a ring that goes around that one. And so it's many, many rings together, infinitely many. We summed them up to find the electric field of a disk. So what's the difference between a disk and a ring? Well, a ring, there is charge only on the ring, here, right on the edge, on the circumference. A disk, it's an area, so there is charge throughout. So a disk charged disk. Remember what eta was. Eta is if you take the charge and divide it by the area. Let me write the word first. Charge over area. So Q divided by A. Charge over area. So what was it? Well, here is a disk. And the disk has radius R. But again, it's a disk, so there is, if you're talking about pluses, there are pluses everywhere on the disk. Okay. And the question is, what is the electric field a distance z away from the center of the ring? And it turns out, I'll try to write this one correctly. It is, the electric field is eta over 2 epsilon naught times 1 minus c over z squared plus r squared squared c and r. Yeah. Hopefully it looks right. Good so. That was for a disk. So we went from a ring to a disk by integrating. Again, we did all that for the discussion. And then we said, how about an infinite sheet of charge? Let's say, instead of just a disk, where let's say you have a charge per unit, let's say it's a coulomb per meter. What if I have an infinite sheet of charge? It's infinitely large, and every meter has charge, let's say 1 coulomb per meter, or per meter squared. So some constant eta, some constant charge density, uniform charge density. What would the electric field be? So an infinite sheet in other words, it's a plane, right? It's a, let's say the XY plane, the whole plane. Or charge density eta. What was the electric field? Well, the trick was we did this. We said, okay, well, just make a disk that's infinitely large. So let the radius of the disk go to infinity. So if you do that, if R goes to infinity, then this part will disappear, become 0, right? You'll be dividing some finite number by an infinite, so you get 0. So you just have a 1 here. So the only thing that stays is eta over 2 epsilon. So for an infinite sheet of charge, the electric field is eta over 2 epsilon naught, no matter how far away you stand from it. So if this, if the chalkboard was an infinitely charged sheet, whether I'm near the board or I'm far away from the board, or I'm even farther, it doesn't matter. The electric field will always be this. Just to emphasize, let's put the word constant. Okay. And so we derived all of this using some integration. Okay. Today we will, or maybe not today, I don't know. We will rederive a couple of them using symmetry. and it would be simple. And then, there is one more, formula that I will state without proof, but when we do Gauss's law, it would be obvious. We will get. So if you have, let's say, either a sphere of charge or a shell. So let's say I have a sphere here of radius r, right? And let's say there is charge. This is a sphere. This is not a ring, this is not a disc, it's actually a ball. Okay? It's a ball and there's charge everywhere within the ball. It's a solid ball, or a spherical shell, or a spherical shell. It doesn't matter if it's radius r. As long as the charge here or here is capital Q, the total charge. A spherical shell means the charge is only on the, like if you have a ball and it has air in it, the material is only on the, like the, what do you call it? Surface? The surface, yes, thank you, that's the word. For this one, the material, the charge is everywhere within it, right? Which is a solid ball, it's like a solid ball, like a bowling ball, right? That one is solid. Basketball is empty from the inside. There's air. So this one is a shell, and this one is a sphere of radius. Anyways, if you're outside, if R is greater than capital R, meaning you're here, you're outside, the question can be, what is the electric field there? Now here is, if you want to do this problem using direct integration, I mean, you would have to divide. Let's say if it's the ball, or since I have R here, let's say it's a spherical shell. I take a dq here, and I say it will produce an electric field here, and it's in this direction. Take this dq here, so it's a different distance, right? Some of them are closer, some are farther, and remember, it's a three-dimensional figure. So some are on the sides, and they produce an electric field this way. Once you add all of those, it will be an integration problem. You will end up with the following. You end up with the electric field equals 1 over 4 pi epsilon naught times the charge on the entire shell or the ball divided by r squared. And this should remind you, as it's just as if it's a charge sitting at the center. So, as long as you're outside, the electric field is as if you have the entire charge at the center. And we dealt with this when we did gravitation, right? We said the gravitational force between, let's say, two planets, it was capital G m1 m2 over r squared, right? And we said the distance, where is it measured from? It was from the center of one planet to the center of the other. It's as if the entire mass was at the center of the planet. And that's a consequence also of Gauss's law. So we're not going to do this using integration, we will do it using Gauss's law a little bit later. But for now, this is the result without proving it. So that's what we did last time. Well, that's everything we did, and this one I just added. I would like to do an example just to ease things and then continue. So here is the example. We have a 10 centimeter diameter disk, so it's a disk of charge. And it's charged uniformly with an extra 10 to the 11 electrons. So you take 10 to the 11 electrons, but it's 100 billion electrons, and you add them on the disk. So the disk is uniformly charged, and it has a total charge of 10 to the 11 electrons. We need to find out what Q is, what the total charge is in a moment. And the question is, it says, what is the E field, what is the electric field, 1 millimeter above the surface at a point near the center. You have a disk, and you're not on the disk, you're 1 millimeter away from the center of the disc. So I'll give you a moment to kind of read it again, and then I want to refer to the picture of the disc there and ask you what you should put or should not put. Ready? So here is a disc. This is the electric field for a disc. Eta is the charge per unit of area. So we need to find eta. 2 epsilon naught, we know what epsilon naught is. It's 8.85 times 10 to the minus 12. 1. R is the radius of the disc. I think they said it's 1 centimeter or 10 centimeters. R is the radius, so it's 10 centimeters or 0.1 meters. And now what is Z though? What would Z be?
The distance away.
The distance away. So Z would be the distance away. So what is Z in this case? What did they call us? 1 millimeter, or 10 to the minus 3, right? 1 millimeter. So that formula says, so here's what we're given. We need to find Q. Q is the total charge due to 10 to the 11 electrons, right? Total charge due to 10 to the 11 electrons. So it will be, how many electrons I have? I have 10 to the 11 of them. That's what they told me. And then times the charge per electron. What is the charge of 1 electron? I know I didn't write the number down.
1.6 10 to the power minus 19.
All right. It is 1.6 times 10 to the minus 19. I know it's negative, but I would just, okay, do this for now. Right, so I'm just interested in magnitudes. Right, so that is Q. So we need to multiply these numbers. So if you do that, you'll get 1.6 times 10 to the minus 8 coulombs. That's the charge. Okay. Next, I need to calculate eta. Eta is the charge density. Eta is the charge over area. The charge is 1.6 times 10 to the minus 8 divided by the area. Well, it's a disk of diameter. Oh yeah, it's a diameter, so divide that by 2 to get the radius. So it's a disk of diameter 10 centimeters. So the area is pi r squared, since it's a disk. So pi r squared. So pi times r squared. So I get 1.6 times 10 to the minus 8 over pi is pi. R is half of 10 centimeters, so 0.05 meters squared. So I think it's 2.04 times 10 to the minus 6. 2.04 times 10 to the minus 6. What units? Yeah. Charge per unit of area, so coulombs per square meter. Coulombs per square meter. Okay. Next, we need to simply plug into that formula to get E. We have eta, we have Z, and we have epsilon naught, so let's write down. So E. And when I'm pointing there, I'm pointing to this. For this. So I'm going to just copy that. So eta over 2 epsilon naught times 1 minus Z over Z squared plus R squared to the power, no, just square root. So here it is. Eta is 2.04 times 10 minus 6 divided by 2 times epsilon naught, which is 8.85 times 10 to the minus 12 times 1 minus, Z is 1 millimeter, we said, right? So it's 0.001 meters. 0.001 over the square root of Z squared. 0.001 squared plus R squared. R is 5 centimeters, so 0.05 squared. I will give you a moment actually to write it down or to plug in the numbers in your calculator. I do have it, but I want you to actually flex something.
How did you get the 8.85? Is that given?
Yeah, it's epsilon naught.
Okay.
Anybody got it?
$7.015 times 10 to the 5th.
7, you said?
Yeah, 7.1015 times 10 to the 5th.
Times 10 to the 6. I have slightly different.
I have 11, or I have 104,000.
Okay,
Yeah,
so something times 10 to the 5th.
Yeah.
Yeah, 113,000.
That's what I have. I have 1.13 times 10 to the 5th.
Yeah.
So just double check. By the way, most of the contribution, you see this is 0.01, 0.05 squared. 0.001 is basically negligible compared to the 0.05 squared. So if you ignore that and take the square root, you just get 0.05 on the bottom. And so you have 0.001 over 0.05, and that's negligible compared to 1. So this whole stuff is basically negligible compared to this. So, yeah. I would write down this one, 1.13 times 10 to the 5th newtons per coulomb. That's the electric field. All right. Does that sound right? Okay. So now the parallel plate capacitor. That's the next topic. Parallel plate capacitor. The capacitor would be an important element in when we do circuits. So a parallel plate capacitor basically consists of 2 plates. It's a plate and a plate that are parallel to each other. Here's a plate, and they are parallel to each other, and they are charged. The distance between them is usually tiny compared to their surface area, compared to their dimensions, length and width. And so they're like really close to each other. So one of them has a plus charge on it, the other one is negatively charged. And we will not worry about how you get them to get charged until when we do currents, we will worry about that. But for now, they are charged somehow. One of them has a plus, the other one has a minus. And the question is, what's the electric field between them? So we're going to assume, since they are plates, they are basically sheets. And I mean, nothing is infinite basically in real life. But we're assuming they are large enough compared to everything else that they are infinite sheets of charge. And we're going to use the following formula. Since they are infinite sheets of charge, approximately, this is the electric field between them. So here's how it looks like. So parallel plate capacitor. So looks. I would attempt to draw in 3D two of them. So here is the first plate. Okay. And the second one is right next to it. It would be here. Okay. And they're a distance d apart. From here to here it's d. The distance between the two plates is d. Each plate will have an area A. So if one of them is positively charged, the other one will be negatively charged. So let's say this one is the plus charge. Usually plus is blue, right? Or red?
Oh.
Blue?
I think so.
Okay. I will put the plus, blue.
I know negative is red.
Or negative blue. Okay. Well, road is red. So minus. So this plate is minus. So that's how they look like when I attempt to draw them in 3D. But for now, from now on, I'm going to just look at side view of them. So you have two sheets and you're looking at them on the side. Okay? You're looking at them on the side. So here's how they look like. So here is the first sheet. And let's say it is positively charged. Red is positive, you said?
That's good.
The both codes? Okay. Red. And then, here's the other one. So each plate has an area A, and it has charge density eta. Right? So this one will have charge density negative eta, and this one will have charge density positive eta, right? Okay. All right. So yeah,
Are you saying theta?
eta.
Sure.
Like this. In Word, if you put /eta, it will write this for you. Yeah.
Is eta interchangeable with sigma?
Yes.
Okay,
Yeah.
thank you.
Most books use sigma,
Okay.
but I'm using the same notation as our author. Yeah. Yeah. So, so those are the charge densities. So now, let's think of the positively charged plate and ask, what's the electric field? Here, here, and here. In what direction is it? And also in what direction, yeah. So let's start with this left side. In what direction is the electric field due to the positive charge? Yeah, electric fields always start from positives. They go away from pluses, right? Electric fields go away from pluses. So here is the electric field. So on this side, it will look like this, right? That's the electric field due to the positive charge. And it is, by the way, equal to eta over, eta over 2 epsilon, right? Because it's an infinitely charged plate. So again, I mean, obviously the plates are not infinite, but they are large enough that we can assume they're infinite. Makes the math easy. So that's the electric field here. How about the electric field here? To the right. How about the electric field in here?
To the right.
It's still to the right, yeah. I mean, it's always away from it, If you're to the right of this plate, the electric field is just away from it. Okay? Now the negatively charged plates, the electric field is negative, so electric fields always go towards them. Electric field lines go towards them. So let's start here. In what direction is the electric field due to this minus? Toward the minus. So where is toward?
Right.
Good, thank you. And then how about here? In what direction is toward?
To the right,
To the right. And how about here? In what direction is towards?
to the left.
Do that. Okay. Now, each of these fields, each of these arrows, has a magnitude of eta over epsilon naught. Eta over 2 epsilon naught. Again, where did I get this from? Where is this formula coming from? For the electric field?
Infinite sheet.
Or an infinite sheet of charge, yeah. So this is the electric field due to the plus charge or the minus charge, either one. The plus or the minus, that's the magnitude of the electric field. So, now, the combination of these two sheets will tell us what the total electric field is. So, let me write it here. The electric field, therefore, is equal to, if you're outside of the plates, if you're outside, or let's start with inside. If you're inside, if you're here, in between the plates, right, inside the two plates. So how much is the electric field inside?
2, or
Yeah.
n over 2, n over epsilon.
So you got a contribution of eta over 2 epsilon naught from this one, and another eta over 2 epsilon naught from this one. You add them together, eta over 2 epsilon naught plus another eta over 2 epsilon naught. What's the total?
Eight over epsilon.
Eta over epsilon. Eta over epsilon naught. Yeah. How about outside?
Oh, no, that's fine. Oh, it's actually
0.
Yeah, you got one of them of eta over epsilon naught to the left, and an eta over I keep saying eta over 2 epsilon naught to the left, eta over 2 epsilon naught to the right. Add them together, you get 0. And the same thing on the right side. So outside, the electric field is simply 0. Zero. Right? Okay. Now, you can write this in a different way, because eta is the charge over area, right? Q over area, charge over area. So eta is Q over the area. Q over the area. So we can write the electric field as, alternatively, the same thing, but just written differently. You can write it as, if you replace eta by Q over A, you would have Q over A times epsilon naught. So it would be Q over epsilon naught times A. This is inside. And then it is 0 outside. Okay. So the net electric field is simply like this. Inside the plates, it's just from plus to minus. That's the electric field. That's the total electric field. Anywhere between the plates. Anywhere outside is 0.